Hello everyone, today I'm going to walk you through how to draw harmonics and fundamental resonant forms for various kinds of tubes, whether it be open-open, open-closed, or closed-closed. I am also going to solve a sample problem that is very similar to your Connect assignment, Chapter 11, Problem number 7. This is also going to be very similar to your Unit 6 lab, so if you have any trouble with waves at all, please continue watching. A 1.6 meter long tube with one closed end vibrates at resonant frequencies of 268 Hz and 375 Hz, with no other resonant frequency between these values. What is the fundamental frequency? Before we even begin to attempt solving this problem, let's talk about the three different scenarios: a closed-closed tube, an open-open tube, and an open-closed tube. Let's start with our first scenario of a closed-closed tube. For a closed end, we know that there must be a node, so there must be a node at both ends in this case. Let's set the length of a tube at a value of x. For our fundamental resonant mode, otherwise known as our first harmonic, we want the fewest possible nodes between the two closed ends. In this case, there would just be a node at one end and a node at the other end. This is so that we can yield the lowest possible frequency. For our second harmonic, we want the second fewest amount of nodes between the closed ends. This is possible by adding another half of a wavelength. We can continue with the same trend for our third and fourth harmonics. Now let's calculate the wavelengths for each of these harmonics. Notice how for our fundamental resonant form, our entire tube makes up for one half of a wavelength. For our second harmonic, the entire tube makes up for 2 half wavelengths. For our third harmonic, the entire tube makes up for 3 half wavelengths, and for the fourth harmonic, the entire tube makes up for 4 half wavelengths. Do you spot a trend? Well, for each successive harmonic, we're squeezing in an additional half of a wavelength. Now let's move on to our second scenario, an open-open tube. For an open-open tube, the two ends must end at an antinode. Let's once again set x as the length of the tube. For our first fundamental mode, we want the fewest amount of nodes between one antinode open end and the other antinode open end. Thus, our fundamental resonant mode would look as such. And like I did for the closed tube, I'm going to draw the second, third, and fourth harmonics for this open-open tube. Keep in mind that the end of each open-open tube must be an antinode. Let's calculate the wavelengths for each of these harmonics again. As shown in the diagram, for our first harmonic, the length of the tube x makes up for 1/2 of a wavelength. For our second harmonic, the length of the tube x makes up for 2 half wavelengths. For our third harmonic, the length of the tube x makes up for 3 half wavelengths, and for our fourth harmonic, x makes up for 4 half wavelengths. Notice again how with the open-open tube, like the closed tube did, for each successive harmonic, an additional half of a wavelength was added. Now let's move on to our final scenario, a closed open tube. This is the scenario that the problem is using. At the closed end of this tube, there must be a node. At the open end, there must be an antinode. The length of our tube is once again x. As always, for our fundamental resonant form, we want the fewest possible number of nodes between the ends, but it still has to satisfy the rule of having a node at the closed end and an antinode at the open end. In this case, our fundamental resonant form would look something like this. I'm going to continue on and draw the first, second, and third overtones. Okay, now let's calculate the wavelengths. The closed open tube is a bit different from the closed and the open tube. For the fundamental resonant form for the closed open tube, the length of the tube, x, makes up for only 1/4 of a wavelength this time. As shown in the diagram, for a closed open tube, for the first overtone, the length of the tube x makes up for 3/4 of a wavelength. In the second overtone, the length of the tube x makes up for 5/4 of a wavelength. And finally, for the third overtone, the length of the tube makes up for 7/4 of a wavelength. And notice between each successive overtone, there was another half of a wavelength squeezed in. This is a characteristic that applies to all kinds of tubes: open, open, and close. Using basic algebra, we can solve for the wavelength. So for the fundamental resonance form, lambda is equal to 4x. In the first overtone, lambda is equal to 4/3 x. In the second overtone, lambda is equal to 4/5 x. And finally, in the third overtone, lambda is equal to 4/7 x. Because this is a system composed of one open end and one closed end, in the fundamental resonant mode, the length of the tube is composed of only 1/4 of a wavelength. Because of this, it's only possible to have odd harmonics. Okay, now let's start solving the problem. Velocity of a wave is equal to its frequency times its wavelength. In this case, the velocity is constant because the velocity in the system is just the speed of sound. Since we're not given the temperature of the air, we cannot figure out what the speed of sound is just quite yet. Anyways, since the velocity is constant, as frequency increases, the wavelength must decrease, and vice versa works as well. As frequency decreases, wavelength must increase to compensate. And thus we can derive an equation. F1 lambda 1 must equal to F2 lambda 2. How do we solve for the wavelength? As shown from above, when you go from one overtone to the next overtone to the next overtone, you're slowly decreasing your wavelength. For instance, when you go from your first overtone to your second overtone, you're changing your lambda from 4/3 x to 4/5 x. And when you go from your second overtone to your third overtone, you're going from 4/5 x to 4/7 x. And so as a general rule, if you start out with one resonant frequency that yields a lambda of x over n, the next immediate resonant frequency will yield a lambda of x over n plus 2. From the problem, we're given that one resonance frequency is at 268 Hz. The next possible resonant frequency is at 375 Hz. Substituting these values in for F1 and F2, we ultimately arrive at a ratio of n plus 2 over n, equaling to 7 over 5. And so what does this ratio tell us? Well, this ratio tells us that when the frequency is equal to 268 Hz, we're at the fifth harmonic and the second overtone. When the frequency is at 375 Hz, we're ultimately at the seventh harmonic and the third overtone. Now let's solve for the speed of sound. Once again, velocity is equal to the frequency and the wavelength. Let's solve for the velocity when frequency is equal to 268 Hz. So let's just first plug that in. What is the wavelength when we're at 268 Hz? Well, we know that 268 Hz yields the fifth harmonic, and at the fifth harmonic, lambda is equal to 4/5 x. So let's plug in 4/5 x, x being the length of the tube. Substituting in 1.6 meters as the length of the tube, we can solve for the speed of sound, and we ultimately get that the speed of sound is equal to 343 meters per second. Now let's solve for our fundamental frequency. 343 meters per second should equal to our fundamental frequency multiplied by the wavelength that the fundamental frequency yields. And from the diagram we drew out, we can figure out that the fundamental frequency wavelength should equal to 4 times the length of the tube. Let's plug in these values. So let's plug in 1.6 as the length of the tube, and we ultimately get that the fundamental frequency is equal to 53.6 Hz. Thanks for watching this video, and please feel free to refer back to this video when you're doing your Connect assignment and when you're doing your lab.